Okay, good morning to everybody. Just a few people today compared to yesterday. I think people enjoyed too much their night in Cambridge. So the first speaker is Valderio Reisen, but I don't think he's here.
Sorry.
Okay.
Good morning, everybody. I didn't realize. I didn't know that.
Yeah. Okay.
Well, the taxi.
Let's just
It's
switch
okay,
it.
we-
You do the second.
Okay, that's okay.
We start then with Yuan Shen, which will talk about variational multi-chain Monte Carlo for inference in partially yourself nonlinear diffusion.
Very good, good. And see.
Yeah.
First, good morning. First, thank for the opportunity to give a talk here. In this talk, I would like to present you so-called variational Markov chain Monte Carlo for Bayesian inference in nonlinear diffusion. And for this inference problem, the state-of-art MCMC algorithm is so-called hybrid Monte Carlo, which combines the molecular dynamic and MCMC. And in this work, we make direct comparison between our algorithm and the hybrid Monte Carlo algorithm. This is a joint work with Professor Opel and Dan and Cedric as well. Here is the outline of my presentation. First, I would like to give a brief introduction to this topic and to put our method into the context. Next, I would like to discuss the general ideas about the variation of MCMC and show how those general ideas can be implemented for nonlinear diffusions. And our algorithm will be demonstrated with by numeric experiment with some two toy systems, and I will finish my presentation with some conclusions and future work. And nonlinear diffusion, mathematical nonlinear diffusion can be described by stochastic differential equations with the derivative is a deterministic nonlinear function f, and in this work, we assume the diffusion matrix D is time independent, state independent, and is known to us. For inference, we have discrete time observations. Again, we assume the measurement function h is null, and we consider an identity function. And we also assume Gaussian observation noise, and the covariance matrix, the error covariance is time independent, is known to us. In this work, we consider two one-dimensional toy examples. The first is double wheel, with first system with double wheel drift, and this system has two stable states, and depending on the value of diffusion coefficient kappa, the system shows different behaviors. For example, the rare transition with kappa equal to 1/2, and frequent transitions with kappa equal to 1. We also, another toy example we consider is the system with sign drift. With this system, we observe not only multiple frequent transitions, but also transitions between many levels. This is clear because the sign drift, the corresponding potential has multiple modes, and depending on the kappa value, with large kappa value, we observe multiple transitions, and the distance between each levels corresponds to 2 pi. And if the kappa value is small, and then the system will stay on one well. And the Bayesian inference for nonlinear diffusion can break down into the prior on the hyperparameter, prior on initial state, and prior on the state that follows the initial, prior on sample path that follows the initial state, and likelihood as well. Due to the Markov property of the nonlinear diffusion, we have this expression for prior on sample path, because we have assumed Gaussian error, observation error, so we have this expression for likelihood. And for this inference problem, we have a variety of computational methods, including exact ones and approximation ones. And the KSP equation is the solution to the above inference problem. But the numeric solution to this PD is intractable. And Markov chain Monte Carlo samples the posterior. Even with state-of-art hybrid Monte Carlo, it is computationally expensive. And now we look at the sequential Monte Carlo smoother or particle smoother. If we look at the example of double well with small diffusion coefficient, and the particle smoother required a large number of particles to achieve a reasonable smoothing estimate. On the other hand, the particle smoother is an n-square problem. Therefore, for this particular problem, a particular example, the particle smoother is even computation more demanding than Markov chain Monte Carlo. And for common type approximation methods, which is still based on the best linear estimation, while taking into account the nonlinear function in the propagating mean and covariance through approximation in one way or another. If we look at ensemble common smoother for our toy example, double well with small diffusion coefficient. The inference problem, simply speaking, inference problems we sample this posterior distribution on state, conditioning on data, or we estimate first mode mean and first moment mean and second moment, for example, marginal covariance from this posterior distribution.
The y's are observed.
Y's is
not some non-linear function of the x, or
y is our observations, discrete time observations. X is the state of our diffusions.
Okay, so the thing you were talking about before was a latent process, a diffusion latent.
Yes, diffusion process.
Non-linear observation of that.
Yes, diffusion process can be seen as a latent process. Yeah. So for our toy example, a double well. For our toy example of double well with small diffusion coefficient, first ensemble common smoother fail to track the transition accurately. The second, the ensemble common smoother sequential smoother, which all smoothing estimate have to be modified when we have a new data. And the variation approximation methods is another direction of making approximation. In particular, the Gaussian process approximation is to approximate the true posterior by a Gaussian ones while while minimizing the chaotic difference between the true and the approximating posteriors. And our variational MCMC actually is a variational GP approximation method assisted MCMC methods. In other words, approximation methods assisted exact methods. Why this idea is promising, then we can see from this picture. This is a comparison of state estimation between MCMC and the variational GP approximation. And the solid line represents the mean estimate, and the shadowed areas represent the twice standard deviation envelope, and the black dots represent our observations. And you can see the blue line represents the results of MCM represents variation GP approximation, and the red line represents the results of MCMC. You can see they have quite a similar the estimate of mean and marginal variance as well. Okay, now I would like to try to discuss the general idea of variation MCMC. The first step is we make a proposal by sampling from approximate posterior distribution. Therefore, it is clear our MCMCs essentially are independent sampler, which is different from hybrid Monte Carlo. In hybrid Monte Carlo, the proposal depends on the current state. Also, the approximate posterior is optimized, but the difference between true and approximate posterior could make the acceptance rate of proposals quite low. This is why the idea of blocking comes into play. Essentially, we subdivided the state vector into several blocks and make a proposal for one block conditioning on another as the remaining blocks. We can understand this way. In this setting, our proposal is no longer completely independent from the current state. And then, which is similar to the hybrid Monte Carlo methods. Therefore, the signs of blocking plays a similar role as step size in random walk samplers. So we can choose the optimal block size using the same idea in random walk sampler. Then the independent sampler has another handicap. If the true posterior has narrow peaks, then the independent sampler could get stuck into these narrow peaks. This is why we need to combine the independent sampler with random walk type sample, for example, hybrid Monte Carlo, to explore this narrow peak in true posterior and get out of this narrow peak. Now, I would like to discuss how those general idea can be implemented for the nonlinear diffusions. First, how we can use the variational GP approximation results to make our proposals. What we get from variational GP approximation results essentially, we have a approximate linear diffusions. A linear diffusion approximates the nonlinear one. And in the linear drift, the trend A and the offset B are the variation estimate following the GP approximation methods. Secondly, we have an approximate posterior on the initial state. We assume the posterior on the initial state is to be Gaussian one, and its mean and variance are the variation estimate as well. Then with those results, we can make proposal simply through simulation. First, we sample the initial state from this Gaussian distribution, and then we can integrate this linear diffusion forward in time. In first two panels of this picture, this is an example of the trend A, variation estimate of trend A, and the variation estimate of offset B for our toy example with double well. And on this panel, I show a sample path from MC results. And suppose this is a realization of a double well SDE. We extract the diffusion contribution and run our approximate linear SDE with those noise terms, which is displayed on the last panel. And if we compare this sample path, we see they share a common structure, but we also see the difference between them during the transitional phase. The second step is how to implement the blocking idea for nonlinear diffusions. Simply, we subdivided the whole smoothing window into blocks, and therefore the whole sample path into a number of subpasses. Then we choose a block randomly and make proposal for the subpath on that block, conditioning on the remaining paths. Due to the Markov property, actually, we make a proposal only conditioning on the points, the last points outside this block on the left side, on the right side. And here, the blue lines is an example of this conditional proposal for this block. Here is another example for conditional proposal. And as see, essentially, it is a problem of simulating the bridging process. Therefore, we need effective linear diffusions with which we can integrate forward in time. And on the other side, we need to meet the fixed point at the end of this block. Simply speaking, we need to find the effective trend A, and effective offset B, and effective diffusion coefficient as well. It turns out it turns out the effective diffusion coefficient is very close to the true one. The most interesting are the effective, the A and effective B. In this picture, we compare the effective A with original A and the effective B with original B. And this picture shows to large extent both are same within a block. Only before the end of block, both A and B increase rapidly, and the increase and the B makes sure the marginal variance will decrease to 0, and the increase of the offset B makes sure that the mean path will be drawn to the fixed point. The last step is how to apply the idea of mixture transition kernel to our nonlinear diffusion problem. In this picture, I plot the trace of MC samples of state at 3 different times within the smoothing window. And you can see this is a time instant within the first stationary phase. This is a time within the transition phase, and this is time in the second stationary phase. And the x-axis is the MC algorithm time. And from this picture, we can see the problem of independent sampler. The independent sampler could get stuck for a long algorithmic time. This is observed for our double-way system with a small diffusion coefficient, but not observed for the other 2 examples with large diffusion coefficient. And the occurrence of this behavior will reduce the efficiency of independent sampler. Therefore, we need to combine in our example, combine with hybrid Monte Carlo. For example, with some certain probability, we run the Markov chain with our independent sampler, and otherwise we will run the hybrid Monte Carlo, so we can remove such behavior. But on the other hand, using of hybrid Monte Carlo will cost extra computational time. In this presentation, I show the results without using this step. Now, I would like to demonstrate our methods with numeric experiment. First, as I said, we make a direct comparison with hybrid Monte Carlo, and for both methods, we run the Markov chain with the same computational time, and then subsample these 2 trains in such a way that we have the same number of samples. And we compare the burn-in period for both methods, as well as the autocorrelation function of some summary statistics for both methods. And we also check the marginal estimate from both methods. And for burn-in period and autocorrelation function, we use the summary statistics L, which just integrate the sample path throughout the window. First, we make a comparison of the burn-in period. on the left panel, I show the results for double well with rare transition, and on the right panel, I show the results for double well with frequent transitions. And on that panel, the dark, the black lines is the result of hybrid Monte Carlo, and the red one is our validation MCMC. And this is a summary status X, a plot of summary status X against the MCMC algorithm time. And it is not a surprise that independent sampler have a much short burn-in period, because we initialize our simulation by simulating the approximate linear diffusions, while in case of hybrid Monte Carlo, we initialize the simulation by simulating simply the stochastic differential equation. And we have the similar picture for the double well with many transitions. Next, we compare the autocorrelation function of summary statistic L for both cases. First, we look at the case with double well, for the double well with rare transitions. This is the plot of autocorrelation function of f against the CPU time split of MCMC updatings. First we see both show the similar decay of autocorrelation functions, which means both methods have comparable mixing properties. But we also see at short time scale, the decay of the L is much faster for our methods than for the validation MC methods than the hybrid Monte Carlo. But when the scale increase, the decay of the L for our methods slows down. This may be caused by the phenomenon we have just talked about. The independent sample could get stuck into some narrow peaks. And for the double well with frequent transitions, we have much better result. And we can see the ACF of autocorrelation function of L for validation methods, which is represented by the red curve, is decay very fast to zero, which clearly outperforms the hybrid Monte Carlos. Finally, we compare the marginal MCMC estimate of state X at a different time instance within the smoothing window. The filled bars represent the results of hybrid Monte Carlo, and the empty bars represent the results of validation MCMC. And those plot of histogram shows that both methods provide a similar distribution, or similar posterior distribution of state X at different time, except for the time instant, which is very close to the initial state. We also noticed in most cases both methods provide the similar sampling results for the large value of, for the value of X, which is far from the mean, which shows both our validation MCMS results give also accurate estimate. And we have a similar picture for the another example, double well with many transitions. We also compare the Boolean and autocorrelation function for the sign drift, and the result of sign drift is very close to set of double well drift with many transitions. We see a very rapid decay of the autocorrelation function for our validation MCMS methods. And for conclusion, we see with the validation MCMS methods, we have much shorter Boolean period, and we have reasonable accurate estimate of marginals. And for the case with large diffusion coefficient, we have better mixing property compared to the hybrid Monte Carlo, where we have both methods have comparable performance for the small diffusion coefficient. For the future work, clearly we need to extend this method to the multivariate system, and we also need to develop an adaptive scheme for the mixture methods, so that we can use the hybrid Monte Carlo only when the sample gets stuck into narrow peaks. Thank you for your attention.
Do you have any question?
How much do you gain over the proposal distribution? Because you showed us picture that the variational approximation was already excellent.
So how?
You start with the variational approximation,
Yes.
which you showed us picture was already very, very good.
Yes. I must say the gain in Boolean period is not very significant. For example, here, say for hybrid Monte Carlo methods, we have Boolean period about, for example, 200 time units. But on the other hand, we see the time scale where the sample are completely decorrelated is also about 100 time unit. Therefore, the gain in Boolean period is not very significant, but the gain in improving mixing is significant. For example, for this example.
I meant in terms of accuracy. So if you just have the variational, that gave you a very good mean. You compared variational with hybrid.
Yes. Now, regarding accuracy, actually, this is the reason why we compare the posterior distribution. Except for the time moments close to the initial state, we have quite accurate compared to hybrid Monte Carlo. We have quite an accurate mean estimate and a variance estimate. Except for the time moment close to the initial window again. Initial state.
Any other question?
I'm so a bit confused what the problem was actually. Is it just that the output is just a noisy version of the input of the X?
The problem is this is our underlying system, which is nonlinear diffusion process or Schott's differential equation. Then we try to infer the state of this underlying process. based on the discrete time observations.
What is H?
Is the measurement function,
What is it?
and in our case, we just consider it as the identity function.
So it is just a noisy version of the.
And noise, yes, but this is not. Yes, in this case, yes.
So your idea is to make a variational approximation to this differential equation based on a linear technique, and then
The idea of this this work is try to make use of results from variation methods for making better proposal in maximum Monte Carlo methods.
and if you were to just initialize your HMC sampler at the solution found from the variational technique, what would happen then?
Yes, if we do so, then the burn-in period for HMC may as short as the variation MCM itself, but this doesn't affect the correlation between samples.
They get improved.
Yes. Instead, the gain in burn-in period is not really significant. Yeah.
No more questions? Okay. Thanks again.